Hi, everyone. Welcome to the next iteration of the Physics Colloquium. We're just going to wait a couple of minutes and then we'll begin. Yeah, we're just waiting a couple of minutes just to make sure कि लोग आराम से join कर लें, and then we begin. So Mansoor, Shoaib Munir is also here in the participants.
Oh,
He
that's
can't
great.
really say hi to you. I've actually gotten him up on the panelists as well. Maybe he joined. Oh, there he is. Now he can speak. Now he can speak. Hi, Shoaib. How are you doing? Yeah, he might not have wanted to talk, so he's still appearing muted right now. Maybe he'll say hi a little later.
Hi, sorry. Hi, Rizwan. Hi, Mansoor.
Hey, how
Can you
you
hear me
doing?
now?
How are you?
Very good. How are you? Good to see you after a long time.
Yeah, it's been a long time. Yes.
Yeah, sorry, I was not prepared for for speaking, so I had my mic on mute because I have some background noise here. But I
Right,
should be
right.
fine.
No, good.
No problem. No problem.
Okay, looking forward.
All right, I think we should begin now. It's been we've given everybody enough of a chance to join in. So welcome everyone, like I said, to the next iteration of the Physics Colloquium. Today we have with us Dr. Mansour Rahman. He and I go back a long time. We've known each other now it seems since forever. So Dr. Mansour got his PhD from the University of Delaware. And then he went on to the University of Basel in Switzerland for a postdoc. After completing his postdoc at Basel, he joined the physics department of Quaid-i-Azam University, and he is there, and he is now an associate professor over there. He works at the interface of cosmology and particle physics. Excellent researcher, great teacher, and hope we'll have a great session today. Over to you, Mansoor.
Okay. Thank you. Thank you, Isban, for the introduction and for having me here. And yeah, Isban, I mean, usually we say that, your teacher is your spiritual father. So in that sense, I mean, Isban is my spiritual brother because we both have the same PhD supervisor. So let's start this talk. Sorry. So the title of the talk, Big Rock and Big Rock and Roll be the super cousin of neutrinos. So in this talk, I will be describing an early epoch of the universe where this super cousin of neutrino will play a crucial role. So in this cartoon, I have tried to mention the important concepts, events, and scales which will be relevant for our later slides. So first of all, at basic level, we have four forces: strong force, nuclear force, weak nuclear force, electromagnetic force, and gravity. We know that electricity and magnetism are combined into electromagnetic force, and whereas the strong force is responsible for binding of nucleons into nucleus for their stability. Weak force is, you can say, responsible for beta decay and for the energy source of, let's say, our sun. And gravity, we all know about gravity. So this gravity is described at the basic level, at the classical level. Gravity is described by the Newton gravitational universal law, and which after Einstein generalized this law and make it consistent with relativity, relativity, and this is described by general theory of relativity. And other similar with other forces, we have uh, modern description of these forces which incorporate quantum mechanics and relativity. We call it quantum field theory description of these forces. So we have the quantum electrodynamics or electromagnetic force, and we also have a and later, I mean, Dr. Abdul Salam and others unified in trying to find the quantum field theory or gauge theory description of these forces. They unified the electromagnetic force and weak force. You can call it into electroweak force. So this is a quantum field theory description of these two forces. And now, I mean, we can also extrapolate this unification. So we expect that we can combine this strong nuclear force. The quantum field theory description of strong nuclear force is called quantum chromodynamics. So we can combine this strong nuclear force with electroweak force into what we can call it grand unified force. I mean, and the theory responsible for that interaction is grand unified theory. And we expect this to happen around a scale which is 10 to the minus 10 to the 16 GeV, giga electron volt. And after that, we expect, and this description actually lacks the gravity because gravity is the weakest. So we expect that gravity can become important at scale around Planck scale, which is defined by 10 to the 18 or 19 GeV. And still, I mean, we don't know about a quantum consistent, I mean, a successful quantum theory of gravity. But we have one candidate string theory, which describe this unification. So there are also a few other things. I mean, you can see some scales. So there is this inflation. This is an accelerated expansion era of early universe, which I mean, whose energy scale is bounded by a guard scale 10 to the 16 or so. And you can also see the energy scale explored by Large Hadron Collider, where I mean two protons collide, and we explored the physics of very small, and this happens around 10 to the 4 GeV. So you can compare these two scale. I will be mostly talking about this scale around 10 to the 16, which is called the Grand Unified Scale. So you can compare these two scale. I mean, currently this LHC is exploring energy around 10 to the 4 GeV, and I will be talking about, I mean, this around 12 order of magnitude higher. I mean, this energy scale is 10 order of magnitude higher. So, and you can also compare this scale to the quantum gravity scale. I mean, we expect that quantum gravity scale will become around 10 to the 18 or 19. And this is 2 to 3 order of magnitude. I mean, this gut scale is 2 to 3 order of magnitude smaller. So we can, I mean, treat our theories, I mean, in some effective description sense, that we can ignore the quantum gravity effects, because this is, I mean, 2 to 3 order of magnitude smaller. This scale is smaller. There is also this Big Bang nucleosynthesis, where, I mean, the light nuclei were formed after the Big Bang, after the 3 minutes of Big Bang. And there is also this cosmic microwave background radiation. These are the relic radiation from the Big Bang, which were decoupled around this 3.8 in 10 to the 5 years. So currently, I mean, standard model of particle physics describe this strong and electroweak force. This is our present understanding of these forces. And this gravity, which lacks, I mean, the quantum description, is described by the general theory of relativity. So for standard model, the matter content, I mean, we have 4 types of particles. You can say one type is quarks, second is leptons, third type is gauge boson, and fourth is the Higgs boson. So leptons are different from quarks in the sense they carry colors. and they participate in the strong interactions, where electrons do not participate in the strong interaction. Gauge bosons, these photon, gluons, Z bosons, they mediate the these forces which I described in the last slide. And Higgs boson is thought to provide the masses to most of these particles, and is a fundamental particle, and it is scalar spin zero particle. These matter fields are spin half particles, and this gauge boson is spin one particle. We have three generation. This is the first generation, second generation, and third generation. If we count the degrees of freedom in uh, one generation, it will turn out to be 15 chiral trees. I will describe it later. So we can make a bound state from quarks, like up, down proton, which is a baryon, and quark anti-quark bound state, which is a meson. So all the ordinary matter we know in the universe are composed of these fundamental particles, and it's interesting to know that this ordinary matter constitute 5% of the universe we know about. So second, the gravity. Gravity is described by the Einstein theory of general relativity, which is actually the relativistic generalization of Newton's gravitational law, which you can write down in differential form like this. Here rho is the mass density, and phi g is the gravitational potential. We make a generalization. So in Einstein theory, I mean, it's a theory, it's a tensor theory, and the right side to have energy momentum tensor, which is describe the energy momentum content of the universe. And on the left side you have some terms which are related to the curvature of space. This g mu nu, it contains the information about the geometry of the space. So this matter actually corresponds to curvature in the space. So matter tells space how to curve, and space tells matter how to move. So this is the description. This is the Einstein point of view of gravity. And here we have constant. I mean, the symmetries allow a constant to present in the equation, which is called the cosmological constant. So we will be discussing this constant in later slide. So combining these two pillars, I mean, the standard model of energy physics and the general theory of relativity with the additional cosmological principle, we obtain hot Big Bang cosmology. So what is the cosmological principle? It says that at sufficiently large scales, the universe looks isotropic and homogeneous. So it looks, I mean, it's the same in every direction at every place. So there is also this American sitcom which has the same name, The Big Bang Theory. And if you watch this television program, you will see a lot of physics jokes moving around. So it's fun to have to watch this program. So let's move on. So there are, I mean, this hot Big Bang cosmology has mainly three important predictions. So one is this expansion of the universe, which was experimentally discovered by the Edwin Hubble. And it says that how galaxies are moving away from each other, and from this expansion you can estimate the age of the universe, which is around 13.8 giga year. Second prediction is the presence of leftover radiation, the cosmic microwave background radiation. So this in 1962 or 1965, Penzias and Wilson actually detected this background radiation, which is actually coming from the Big Bang, and their power spectrum matches with the power spectrum of black body radiation, which is at temperature around 3 Kelvin. So this force then actually favors the theory of Big Bang, Big Bang theory proposed by Gamow, Alpern, Bethe. And over the years, this spectrum, I mean, this noise, the cosmic microwave background noise has been detected with increased sensitivity. So you can see this map in 1962. It was Penzias and Wilson, and after that in 1989, the Kobe satellite did a better job, and after that It was WMAP. This was a time when I was doing my PhD in Delaware, and you can see these different regions are actually showing you the temperature anisotropy. Uh, uh, on the average temperature, thick L1, there is a plus minus some fluctuations which are shown by this red and blue spots. So after that, when I was about to complete my PhD and during my postdoc, and after that, this Planck satellite did a better job. So this is the temperature anisotropy map. So every temperature is 3 Kelvin, and there is a tiny fluctuation, temperature fluctuation of order 10 to the minus 5. So, I mean, in this map is actually, you can compare it with the world map. I mean, so you have a latitude, altitude, and you can see the Pakistan here, and maybe you can see the lumps here. I mean, so this point correspond to this point. I mean, so this is a full sky map. The cosmic microwave radiation are coming from all direction, and if you see it, I mean, from the, let's say from the lump, maybe it is a cold spot or hot spot. And you can even detect this cosmic microwave background radiation with your TV set. I mean, about 1% of static noise in your TV set is coming from this cosmic microwave background radiation. So third prediction is the Big Bang nucleosynthesis. Actually, this Big Bang model was proposed by this Alper Bethe Camo, and you can, using their model, you can predict the concentration of light nuclei like helium 4, 3, and 7. So the interesting thing is, I mean, with only one parameter, you can fix, I mean, all these concentration, and that parameter is baryon to photon ratio. Baryon to photon ratio, which is represented by eta. It turns out to be 6 into 10 to the minus 10, and you can see, you can predict the concentration of these light nuclei, and from this concentration you can also estimate that the ordinary matter is actually about 5% of ordinary matter is present in our universe. Also, you can see, I mean, in this baryon photon ratio, it also tells you that there is matter anti-matter asymmetry. There is a matter anti-matter asymmetry, I mean, or which is described by this parameter eta. And so we see only matter around, and we expect these two, matter and antimatter, to be present in early universe with equal amount. So why do we expect that? I mean, you see, if you combine quantum mechanics and relativity, so the ultimate consequence of this combination is that each particle has its own each particle has its I mean, antiparticle. So, I mean, and we expect, and our quantum theory description treats this particle and particle on equal footing. So we expect, I mean, these two matter and antimatter to be present with equal amount. So that's why do we get more matter or more baryons in the present universe. So we will talk about this issue in the later slide. So we will describe matter antimatter asymmetry. You can also call it baryon asymmetry. So with this cosmological principle that our universe is isotropic and homogeneous, you can write down the metric which defines the geometry of the our universe or space. So here, I mean, you can see this is time. These are distance of 3 space in spherical coordinates, and there is a scale factor. The scale factor only depends on time, and it doesn't depend on r and theta phi, because our universe is homogeneous and isotropic. So it's expanding in the same I mean, in the same way in all portion of the universe, and also in all directions. So it's behaving same. So I have, I mean, just to simplify the discussion, I have taken this k equal to 0, which correspond to flat universe. K is the curvature of 3 space. So here, I mean, these coordinates do not see A, so these are called co-moving coordinates. And you can also define physical coordinates, which by multiplying A with these co-moving coordinates. So these are the physical coordinates, I mean, which actually experience this expansion. So using this metric and the energy momentum tensor of a perfect fluid, we can solve Einstein equation, and we obtain two equations which are called Rehman equation. So one equation told you that this Hubble parameter, Hubble expansion, is actually related to the matter content of the universe. This is the energy density, and this is the pressure. So second equation tells you how that expansion actually is I mean occurring. I mean, it is accelerated expansion or deaccelerated expansion. So if rho plus 3p is positive, then it is deaccelerated expansion, and if rho plus 3p is negative, then it's deaccelerated, it's accelerated expansion. So a relation between rho and p is called the equation of state of this universe. So here I've defined this critical value for rho, which is 3s square over 8 pi g, and so current standard model meant, sorry.
Can you hear me? I'm gonna stop you here for just a second. Somebody asked a question in the Q&A. The question is, what is a perfect fluid in this context? And I thought that you should answer this question right now instead of leaving it to the end.
I couldn't hear you. I mean, what was the question?
The question is,
let me see it.
What is
a perfect fluid in this context? So perfect fluid, I mean, you can define it like this. In the rest frame of that fluid should be homogeneous and isotropic. That would be a perfect fluid. So it will be defined by pressure and energy density. So because I mean, your metric is isotropic and homogeneous, your TME new energy momentum tensor should also be, I mean, isotropic and homogeneous. So perfect fluid, according to Weinberg, is when you go to its rest frame or co-moving frame, it is homogeneous and isotropic. So this rho and p will only depend on time. I hope I have answered that question. So next, I mean, this is the fitting model. I mean, you can say fitting model or the concordance model of this modern cosmology, which is called lambda CDM. Here lambda stands for, I mean, dark energy. Lambda is a cosmological constant which appeared in the Einstein equation, and we will be fitting this dark energy part, this which is 68.3% with this lambda. So I said fitting. I mean, we will not be explaining why there is this kind of dark energy, because in a quantum field theory description there is an issue, but I will not be describing that issue. So there is ordinary matter, which is about 5%, and there is this dark matter. This dark matter is actually different from ordinary matter because it doesn't interact with light. So and this CDM means the cold dark matter, which actually describe, I mean, the particles which are responsible for making this dark matter have tiny velocities. Tiny velocities means their velocities are non-relativistic. They are moving slow with respect to speed of light. So this is the energy content, and our current standard model can only describe this ordinary matter. It cannot describe this dark matter and also this dark energy phase. But for this talk, I mean, we will assume that this lambda will take care of this dark energy stuff, and we will be mostly concerned with dark matter stuff. For which, I mean, we will have to go beyond the standard model of high energy physics, which I will describe later. I will be describing grand unified theories where and the supersymmetry, where you can incorporate this dark matter. So I mean, this lambda CDM model actually it's the simplest version of this lambda CDM model. You can say base lambda CDM model. It says this dark matter plus baryonic matter plus cold matter equals to 1. Their density, their relative density, this omega parameter is actually the density with respect to critical density. So this is equal to 1. and they fit the CMB data, the data coming from cosmic microwave background radiation with 6 parameters. So this baryonic part, cold dark matter part, there is a theta angle, tau parameter, and this amplitude of scalar perturbation and its spectral index. So mainly there are two types of this 6 parameter. One correspond to background cosmology, and these few parameters are related to astrophysics, and this is the fluctuation over that background. I mean, how does the primordial fluctuation this behaves, its amplitude and its behavior with respect to different scales. So I will be talking about these things later. So these are 6 parameter fit. I mean, so where does, I mean, this fitting parameter, where does it come from? So what's the physics, I mean, actual physics behind us, which how we can connect it with what we already know, like general theory of relativity and this standard model. So, I mean, when we know how does these different components scale with the expansion of the universe. So one length scales like factor of A. So for radiation, I mean, let's say for matter, you have, let's say, mass divided by volume. So it scales like A to the -3. But in radiation, you get an extra factor of scaling, which comes from the wavelength. I mean, so it has higher level of separation, A to the -4, whereas this density coming from cosmological constant is actually constant. It doesn't scale. So currently we know the content of all these components, so we can just extrapolate uh, these lines back in time, and we can say that at very early time our universe will be radiation dominated. So currently we have these, and you can estimate that our universe will be radiation dominated. So this is actually the initial conditions of hard Big Bang model, which has few problems, and I will describe some of them. One of the important problem is horizon problem. So if you take the radial motion of the light, so your metric will become like this. You will only have this radial part, and if you take this scale factor common, you can redefine your time with a d tau. So this is the definition of this tau, which is also called conformal time. So making this transformation actually helps in talking about the causal structure of this metric, because now, I mean, this thing has become very similar to your Minkowski space, I mean, where you have studied this light cone in relativity. So now a simple light cone, you can draw a light cone, and it tells you that the causal structure, I mean, the things which are like inside the cone can be, I mean, can develop the causal structure. So here we have representative. We are here. I mean, here we have a satellite which are detecting the cosmic microwave background radiation coming from, let's say, at early time. This is the last scattering surface where the cosmic radiations decoupled from the matter. So if we see the light into opposite direction in the sky, let's say coming from here, from the tip of this cone and from the tip of this cone, and we see at this point that the temperature of this radiation is actually around 3 Kelvin. But we see that these two cones do not get, I mean, enough time to talk to each other to develop a causal structure with each other, starting from the Big Bang t equal to 0. So this is issue. Why do we expect that this temperature, I mean, the temperature of cosmic microwave background radiation is so uniform on large scale? So this is a puzzle. And this puzzle is somehow related with this. If you can write down this definition in terms of 1 over ah, which is the actually the co-moving horizon. So if co-moving horizon, whether co-moving horizon is decreasing or increasing, you will see that the resolution of this horizon problem is linked with this concept. Second thing, I mean, if you have a perfectly homogeneous universe, then there will be no structure and no CMB and isotropy. You see the tiny temperature and isotropies of order 10 to the minus 5 who cannot explain this. So we need a mechanism, I mean, which can generate these anisotropy. We can understand this temperature and anisotropy in terms of density and anisotropies, because the radiation and matter was coupled at early time. But what's the origin of these? I mean, this matter radiation, and how to explain this number 10 to the minus 5. So these two questions should be addressed, which is not answered in hot Big Bang model. So inflation can address these questions. So inflation is actually an era of accelerated expansion in the very early universe. And you will see that a deaccelerated co-moving horizon is 1 over ah is co-moving horizon. A deaccelerated co-moving horizon can answer all of the question. I mean, this the horizon problem, for example, which I discussed in the previous slides. So, and this definition also equivalent to a double dot greater than 0, which is an accelerated expansion. Both are equivalent. And if you use the second Friedman equation, this tells you that this pressure is actually negative. You need a negative pressure which corresponds to impulsive gravity. So all these definitions are equivalent for inflation. So how do we connect inflation, this accelerated expansion phase, with the model of particle physics? So in particle physics, we have Lagrangian kinetic energy, potential energy. So you can see. So let's consider homogeneous scalar field, which depends on time only, and it's moving slowly. So you can calculate its pressure and density. Pressure is kinetic energy density minus potential energy density, and rho is like kinetic energy density plus potential. And if this kinetic energy density is subdominant, then you have minus P over P, which is minus 1. So P over rho equals to minus 1. This satisfies this relation, less than minus 1 by 3. And this corresponds to exponential expansion. This exponential expansion, you can take two derivatives. It's actually accelerated expansion, where h is nearly constant and h Hubble parameter is described by the potential of this field, which we call it inflaton field. So the field which is responsible for this accelerated expansion, we call it inflaton. So message, I mean, the message of this calculation is the slow rolling scalar field acts as an inflaton. So that's why I use the word rock and roll. So there is this inflaton, this field will be doing slow rolling, and after slow rolling, it will also be oscillating. That's why we use that word rock and roll. And the inflaton, which particle will be playing the role of inflaton, and that will be super part of neutrinos, which I will describe later. So, and so this is for slow rolling condition. You can write this condition in terms of potential. So this is the one derivative. I mean, it's like kinetic energy term. It's like acceleration. So you can define this one derivative parameter epsilon and two derivative parameter beta. These two parameters should be less than 1. If these two parameters are less than 1, then you get this inflation, and inflation ends when either of these parameters becomes 1. So how do we solve this horizon problem? So I have already told you that this 1 over ah decreasing horizon phase can be important in solving the horizon problem. And this tau actually tells you the size of the causally connected region. So you can see here, I mean, at present time, this dark energy stuff is dominant, and then matter, by matter I mean both ordinary and dark matter. And at later time, the radiation is the dominant component, which is actually the initial condition for Big Bang cosmology. So if we have an early phase of inflation, so it will be, this curve is actually the co-moving horizon. So you will have a decreasing co-moving horizon, and this is the phase of inflation. And you can see, I mean, the scale which we see today, I mean, which were not causally connected at the time of, I mean, the radiation which was coming from the last scattering surface, the decoupling, were not in causal connection. Now they can have a causal connection because this co-moving horizon size is greater than the biggest size of our universe, which is the current horizon. So this is the current horizon size, and this co-moving horizon size is, I mean, greater than this scale. So this thing, I mean, in this way, I mean, inflation solves the horizon problem. And how much inflation do we need to solve this problem? We parameterize this amount of inflation in terms of number of e-folds. So e to the power 50 or 60. I mean, we need that much stretching of the scale factor, e to the power 50 or 60. 50 to 60 e-folds are enough to solve this problem, the horizon problem. So what's the origin of structure formation? So now we have quantum field theory, we have particle physics quantum field theory description. So our inflaton field has quantum fluctuations, and these quantum fluctuations, not only quantum fluctuations in inflaton field, we also have quantum fluctuation in the metric. So these two, this is the scalar part, this is a tensor fluctuation, this is a scalar perturbation. So these both actually contribute to the scalar fluctuation. And during inflation, this quantum fluctuation becomes the macroscopic cosmological perturbation in the density. And this density is then introduced, I mean, or leaves its imprints of this temperature anisotropy in the cosmic microwave background radiation. So we see this 10 to the minus 5. The origin of this cosmic microwave anisotropy is actually the quantum fluctuation in the fields, and also the origin of the structure we see around it. So not only density perturbation, we also have another important information in cosmic microwave background radiation, because these are electromagnetic radiation, so they have polarization pattern. So there are two types of polarization pattern. One is E-like and other one is B-like. So this is E-like polarization pattern, this is B-like. So I mean, they are different from each other due to their handedness. So if you put a mirror, I mean, beside this pattern, it will map into itself, and this also holds for this pattern. But this one, I mean, it changes. I mean, this pattern maps into this one, and this one maps into this one. This shows a chiral behavior in the mirror. So under mirror reflection. So P, that's why we call it P, because P magnetic field also is different from electric field E under parity. So I mean this, and now I mean at fundamental level we have inflaton field and the metric, and this correspond to scalar and tensor fluctuation. So for temperature anisotropy and for E-like polarization pattern only, you can see, I mean, both scalar and tensor fluctuation contributes, but for B mode polarization only tensor fluctuations contribute. So it means if we see this B mode polarization pattern in the cosmic microwave background anisotropies, then it will tell you that there are some, I mean, the gravity is quantized. You will have this you will have, I mean, this B mode polarization will be a great evidence, I mean a strong evidence for inflation itself. It will also correspond to primordial gravitational waves. So this is very important. And yeah, okay, let's see. So now I will talk about some basic inflation parameters which will be useful for our I mean later discussion. So as we saw, there are two types of fluctuations. So there are two types of power spectrum. One is scalar power spectrum and another one is tensor power spectrum. You can parameterize this power spectrum in terms of their amplitudes, scalar power spectrum amplitude, tensor power spectrum amplitude, and their behavior with respect to, let's say K is a wave number with respect to scaling. I mean, how does these fluctuations scale? These are described by their spectral indices. NS is scalar spectral index, NT is tensor spectral index, and NS equals to 1, it means the scalar fluctuation is scale invariant. So it was, I mean, at early times it was thought that ns will be equals to 1, but now, I mean, the experiment has ruled out this possibility at maybe 8 sigma level or so. So in using this slow roll approximation, you can write down ns like this and t like this, and you can take the ratio of these amplitude, which is called tensor to scalar ratio, and it actually gives you an idea of the primordial gravitational waves. So it's a parameter which parameterizes the primordial gravitational wave. Because we have not seen this tensor fluctuation, we have not detected, we have not seen B mode polarization. So there is a bound on this parameter, which is around 0.07. So once we detect primordial gravitational waves through B mode polarization, this will fix the value of R, and also, so also, I mean, you can relate this thing with the energy scale of inflation. Once you know the value of R, you will see that energy scale of inflation is around that scale. Currently, we have a bound, so still the bound is around that scale, 3 into 10 to the 16, and R is less than 0.07. We need 50 to 60 folds, and we can calculate it once we know the potential.
Sorry, can I quickly stop you here, Mansoor? So these B mode polarizations observed by what was a collaboration some years ago, have they completely been ruled out?
Yeah, there was a hype. I mean, that this bicep has
Exactly, bicep,
detected
yeah.
this, B mode
So they've been
polarization.
completely ruled out now.
Yeah, that is completely ruled out, because, I mean, in order to make that prediction, you need to understand the foreground. I mean, and they
Sure.
did not take into account, I mean, some model of background, I mean, this foreground, and once they included that model, I mean, so that B mode polarization went away. I mean, because this foreground
Okay.
can also introduce these B mode polarization things like that.
Of course, yeah, I heard about that. I wasn't sure that it's like they've
Yeah,
completely
so that's gone. I
ruled
mean,
it out.
yeah,
Okay.
that's gone.
Okay, unfortunate. Okay, thanks.
Yeah. So there is this, I mean, late Professor Hawking has a batting over this measurement of this primordial gravitational wave. He thinks his model, I mean, his model can explain the value of R at 5% and above. So he has a bet with the Neathorpe, which has his own model, I mean, aquatic model or cyclic universe model, which does not predict any gravitational waves. So they both have a bet over this. I mean, but I don't know what will be the situation after the death of Professor Stephen Hawking. So current situation from Planck data is here. I mean, because you don't see the primordial gravitational waves, so there are bounds. I mean, so here on the x-axis we have spectral index, on the vertical axis we have tensor to scalar ratio, and these are bounds from Planck and some other experiments. And Stephen Hawking prediction says that it should be, I mean, detected at 5% above. So the most, I mean, restricted bound, if you see this 1 sigma bound is going below this bound. I mean, and this ns equals to 1 spectrum, I mean, which was called the scale independent Harrison-Zaldovich spectrum. Now it is ruled out at, I think, more than 6 or 7 sigma level. So this is the current situation. So we can see various simple, I mean, potential, like polynomial potential, quadratic potential, or quadratic potential. You see, I mean, their predictions are now, I mean, are about to rule out. This lambda 5 force is ruled out at more than 5 sigma level. So this is for 50 fold, and this dot is for 60 fold. For 50 to 60 fold, I mean, the prediction of 5-fold model is ruled out, and this quadratic model is about to rule out. It's just touching, I mean, outside the 2 sigma level of Planck data. So the most popular potential in particle physics is the Higgs potential. So let's consider a simple Higgs potential, a kind of Y model where, I mean, we consider a gauge singlet field. Actually, the Higgs field is not a gauge singlet field; it's transformed under electroweak group. So let's consider a gauge singlet Higgs field. So you have a potential, and it has a wave vacuum expectation value. This wave is m. So you can rock and roll from either side of this potential, either above the wave or below the wave. But you see, uh, the st the steeper the potential you have, it will correspond to large values of R which are ruled out. So that's why Planck data prefers, some word, less steeper potential, flat potential. So it favors the below the wave inflation. So for below the wave inflation, this is near the wave, it corresponds to quadratic potential. And here it becomes, for when phi is much greater than m, it becomes phi 4, which I have shown you that it is ruled out. So for large field models or above the wave field is ruled out, and near the wave it is quadratic, and below the wave you can have, you can partially have prediction consistent with Planck data. You can see this, for 50 or 60 they are lying inside this bound. So we have this thing, but if so, the only field we can think of in standard model for inflation, that would be Higgs, because it is the only scalar particle. For inflation, you need a scalar particle, because if there is a spin, it will introduce an isotropy in the temperature, because we on the large scale we see the temperature is isotropic. So this is the simplest choice. So the only spin zero field is standard model. So can we realize inflation with standard model? With this toy model, you can see that uh, the web of standard model, this Higgs potential is around 100 Chev, and the field which will be doing inflation is much greater than this 100 Chev. So approximately this the standard model Higgs potential will be like lambda phi 4. If it is lambda phi 4, it will give you the value of lambda 10 to the minus 13, and the mass value is 10 to the minus 4. So two problems. Even if you do inflation, it can do inflation, but it is inconsistent. The predictions are inconsistent with Planck data experiment. Second thing, the mass is very much less than 125 Chev, which is we have experimentally measured 125 Chev Higgs mass. So these two problems. So, and another problem is that if you consider 125 Chev, your potential is also not stable around, let's say, 10 to the 11 Chev or so, because we are usually doing inflation around 10 to the 16. So in order to slow roll towards the true vacuum, so you will be here, but you will be rolling in the wrong direction, maybe in the metastable or stable. So this is another problem for standard model Higgs inflation. So I will now move on to physics beyond standard model, and for that we will be considering grand unified theories, and what are the hints or attractive feature of grand unified theories. It offers you to unify all three gauge couplings of the standard model, let's say around 10 to the 16. It happens in the minimal supersymmetric standard model, which I will describe briefly in the next slide. And you see there are different quarks and leptons. This you can unify into fewer number of multiplets. So in SU5 cut or flipped SU5 cut, you only need only three representation, let's say only 2, 10, 5 bar. You can combine 15 chiral fields or 15 degrees of freedom of standard model into these two multiplets. And if you also include right-handed neutrino, so then you have this 10 plus 5 plus 1, total 16 degrees of freedom, chiral degrees of freedom. In Patis-Lamb model, actually Patis-Lamb model was the first grand unified model. So you have this 4 to 1 and 4 bar 1 2. It incorporates the right-handed neutrino. It requires a right-handed neutrino actually. Here, if you don't add right-handed neutrino, no problem. But here, you have to include it because the gauge symmetry requires it. So it has 16 degrees of freedom, 4 to the 8, 4 to the 8, and similar with SO10 special orthogonal 10 group grand unified group. you can include all, I mean, matter into one representation 16. So once, I mean, while unifying these different multiplets into a gut multiplets, you also get some connection between the masses of the particles. This is called Yukawa unification. So you can understand in this framework, you can understand the hierarchy you observed in the masses of quarks and leptons. Leptons are light, quarks and heavy. Why it is so? So you can address this question in this grand unified framework. Another thing, I mean, why neutrinos are, I mean, light. You can explain this thing with a seesaw mechanism where you introduce a heavy right-handed neutrino. At that heavy right-handed neutrino actually happens to be close to the grand unified scale. So this I will also describe later. Another thing, I mean, the energy scale of inflation is also around that scale. This is also important thing. And charge quantization by charge of proton is equal and opposite to the charge of electron. Is related to a question charge quantization, and you can address these questions in a simple grand unified model like SO10 and SU5. Even Islam charge is quantized. You can explain it in this framework. So, I mean, this grand unified theory becomes more interesting when you combine it with supersymmetry. And supersymmetry is the symmetry between fermion and boson. And low energy supersymmetry is attractive for some technical reason. I will describe only, I mean, non-technical things. Let's say, I mean, with supersymmetric models, you can easily get a candidate of cold dark matter. It is the lightest supersymmetric particle is stable. So we impose an R parity, which makes it stable. So, and we also have, I mean, super partners, let's say super partners of standard model particles. You have, I mean, this super partner of up type. So this is S quarks and super partners of these leptons. You have gauge-genos for gauge particles, and for Higgs, you have Higgs-geno. So similarly, I mean, if we add a neutrino, right-handed neutrino, we will have a super partner of a neutrino, which we can call it neutrino. So neutrino is super cousin of neutrino, which will be playing a role. So now, I mean, with this fermions, you have scalars, and scalars can play a role of inflaton. I mean, now we have a lot of candidates. So I will be describing the neutrino as a possibility, a realistic possibility for realizing inflation. So another important thing, I mean, with supersymmetry, your gauge couplings get unified. In standard model, we don't have gauge coupling unification, but with supersymmetry, if we supersymmetrize our standard model, which is called minimal supersymmetric standard model, we obtain gauge coupling unification, and it happens around this 10 to the 16 scale. So this is interesting. So supersymmetric guts are interesting. I mean, it automatically gives you gauge coupling unification. So now I will be describing the supersymmetric models of hybrid inflation. In supersymmetry, we have superpotential instead of potential, and this hybrid inflation model, supersymmetric hybrid inflation model, was proposed by Diwali, Shafi, Schaeffer, separately from Copeland, Little Lights, and Stewart bonds. And here we have a gauge singlet superfield. So, and the scalar part of the superfield, scalar component of the superfield actually plays the role of inflaton. And then we have two fields which are conjugate to each other under some group J. And the R symmetry, which restricts the structure of the superpotential, and which makes this superpotential lineariness. If you add, I mean, cubic or quadratic terms, then it's bad for inflation. So this discussion will be a bit technical, somewhat technical. And but I mean, with this symmetry, we get, I mean, the superpotential at renormalizable level. I mean, it has very unique form and very simple form. So this idea is very, I mean, attractive, as we will see that the inflation, you can associate inflation with with some symmetry breaking. G goes to H. So how do we see that? So here are few example of the gauge groups we can consider. We can consider P minus L extension of the standard model. We can have SU5, flipped SU5, Islam model, or SO10. I will be considering specifically U1 B minus L extension of standard model, which can be embedded in SO10. Okay, so we can calculate potential from superpotential, and you can see its form. You have two fields. One is Higgs field. This phi is Higgs field, and another one is S field. So we do at early time, I mean, we do inflation in this valley. This here we have slow roll inflation, and then here we have fast inflation. So this ends the inflation. This is called the waterfall effect. So this valley becomes a hill. I mean, so you have inflation. You can also think we can also treat this as field like a temperature. So in early time, temperature was very high, and then after that, at some point, at some critical point, temperature falls below some critical value, which is this M, and the symmetry is broken. So this is a second order, I mean, symmetry breaking phase. I mean, and the gauge symmetry, underlying gauge symmetry is broken. So after the end of inflation, the gauge symmetry is broken. So this is the idea that you can associate inflation with the gauge symmetry. So during inflation, I mean, you can see S is 0. When S is 0, phi is 0. When phi is 0, you have a very flat potential. So we need some slope in order to have some slow rolling, which is actually provided by the splitting in the supermultiplets. Because during inflation, potential is non-zero, supersymmetry is broken. When supersymmetry is broken, so it introduces a splitting between fermions and bosons. So this is the splitting proportional to this symmetry breaking kappa square M4. So there is a splitting, and this splitting between fermions and boson actually contributes through quantum correction, through loop correction, and it can give you slope, like, I mean, it introduces in otherwise a flat potential logarithmic varying function, I mean, slowly varying function. So it provides you slope suitable for inflation. So with this model, we can see the prediction ns versus, let's say, kappa. Kappa is actually parameterizing this radiative correction. When kappa is very small, you have flat potential, otherwise you have slope. So when kappa is very small, you have ns equals to 1, and when kappa is a bit larger, the curve goes down, but it does not correspond, I mean, it does not lie inside the current Planck zone. Here, the attractive feature of this model is that this delta T over T can be written down like this: M over M Planck, and M is the gauge symmetry breaking scale. You know the size of M Planck. You know the delta T over T, 10 to the minus 8. You can see that M should be around that scale, 10 to the 16. So now including, I mean, there's another contribution apart from radiative correction, that is called supergravity corrections. And for that, you consider the scalar potential. So this is a supergravity correction, and it makes supergravity correction makes the things even worse. This green curve is going up. Also, I mean, deviation is large from Planck. And then there is a third contribution, which is coming from Savsuti breaking terms. This is Savsuti breaking term written in blue color. Blue is Sugra and red is. So including all these contribution, now we can see that these prediction are consistent with Planck data. So Savsuti breaking term actually makes, I mean, play an important role, a crucial role in making prediction consistent with Planck data. So next, I mean, if you consider non-minimal terms in the Kähler potential, you have more freedom, you have more parameter, you have more freedom, you can have very good result. I mean, you can even have the value of M around 10 to the 16, and the value of R large enough to be detected in the future experiment. So as a second important extension, the extension of this hybrid inflation is hybrid model, where we include this term. So now there is this S field, which was inflaton in the previous case, this Higgs field, which is associated, I mean, with some gut breaking, and there is this another phi field. This phi field, now we have three fields, that's why we called it hybrid model. Now this field will be inflaton. In this structure, I mean, you can also study matter field. The matter fields to be inflaton, like super partner of neutrino, neutrino. which was not possible with this field, I mean, in this framework. So this extension makes it possible that you can also realize the super partners, I mean the scalar matter fields, which we have in supersymmetry. So this is the important thing. So here, I mean, the S field is stabilized and the potential becomes very similar to the hybrid inflation potential, which has a waterfall effect. I mean, and so I will be considering, I mean, this B minus extension of the MSSM. Here you can see B minus L extension of the MSSM actually requires this presence of right-handed neutrino due to gauge anomaly cancellation. So we have these right-handed neutrinos fields, I mean, and the scalar partner of this right-handed neutrino fields will play the role of inflaton. Not only inflation, I mean, it is because of neutrino, it also connected with neutrino physics. For example, we can explain the light neutrino masses through Seesaw mechanisms. We have these two terms. We have a right-handed neutrino mass term, and we have this interaction, Yukawa interaction, and we can write down the mass matrix where we have this no left mass, right mass, left mass is actually Dirac mass, which comes from this term. And when these two masses are small, Dirac mass is small as compared to Majorana right-handed mass, then you can explain the tiny non-zero mass of the neutrino. So this guy is the heavy right-handed neutrino mass, and this one is smaller. So through Seesaw mechanism you can explain, and the super cousin of this guy will be doing the inflation, because this is a fermionic field, and super partner, this neutrino will be a scalar field. So there's also leptogenesis, I mean, because these terms break the lepton number, and with the interference of this tree level and the loop level term, you can introduce asymmetry in the leptons. I mean, so lepton and anti-lepton behaves differently, and this asymmetry you can transform into baryon asymmetry through this Faleron process, which is a non-perturbative process. Here you have leptons, here you have baryons. So this asymmetry transformed into baryons, and that baryon asymmetry means a matter antimatter asymmetry you can explain. So in our model, I mean, we have this B minus L extension, we have superpotential, and here you can see right-handed neutrino mass term. And from superpotential, we can have potential. It has two parts, D term, F term. So it's this is a bit technical, I mean, for general audience. So D term we actually get rid of because it corresponds to very steep potential. So we align all these fields along this. So this is the T flat direction, and we use F term, F part of the potential for inflation. So as field is stabilized, we have two field model. You can see its shape is very similar to hybrid inflation model, two field model. But here, I mean, the inflaton, the Y field, this field is neutrino, and this is the Higgs field part. So here we have predictions. We have two cases. In one case, the value of R is a bit small, the tensor to scalar ratio, and the value of M is also a bit smaller than 10 to the 16. So, but in other model, in the other choice of the parameter, we can get this tensor to scalar ratio in the range where it will be detecting, or it will be it has potential. I mean, I mean, it will be detecting future experiment. Good. So M, the value of M is around 10 to the 16. I mean, you can have in this parametric region, because I'm running out of the time. So the value of M, the right-handed mass of the right-hand neutrino turns out to be around 10 to the 14, a bit smaller than gut scale. So this is good. And here you can see the baryon asymmetry gets converted into lepton asymmetry gets converted into baryon asymmetry. And so, and we can embed this B minus L extension extension of standard model into SO10. And here I have described how you can do that. This SO10 group will be broken with 45 representation into this standard model class U1 chi, and then a template will break this U1 chi, and you will get at low energy you will get standard model. the sky charge is related to hypercharge and B minus L. But in our model, effectively, the sky charge is B minus L, because in our model, the inflaton field is a neutrino, which has zero hypercharge, and the Higgs field, which is responsible for breaking B minus L, is actually has hypercharge zero effect. So effectively, the sky is actually B minus L for us. So this corresponds to B minus L extension of standard model embedded in SO10. Your matter field, all matter field plus right-handed fields can be embedded in 16. B minus L Higgs field can be embedded in 16 plus 16 bar, and the electroweak Higgs doublet can be embedded in 10 plus. So there is another model which I will not describe now, but you can also realize this neutrino inflation SU5, and but in SU5 this you can always add this. This is not very connected with the rest of the theory. And in SO10 we have monopole, so we need a shifted track. We need to break the symmetry during inflation so that this monopole problem gets inflated away. So we have this shifted track, we have the inflation here, and then there is a waterfall. So that's all. So here's a summary or conclusion. So our main goal is to find a standard model of inflationary cosmology, and in that direction, we see that this supersymmetric hybrid inflation model actually provides a natural framework for physics beyond standard model, which is in our case is the grand unified theories. And an extension of this sweet hybrid inflation model, that is the tribrid inflation model, makes it possible to realize matter fields for inflation like neutrino. You can also use other gauge invariant combination of other superpartners. And we need more data, more precise data for these spectral indices, for running of spectral indices and other parameters in order to discriminate various models of inflation. And particularly we need, the B morpholization data, which these future experiment, Pixie or Prism, Lightbird, will be doing in future. So I will stop here. Thanks for your attention.
Thank you very much, Mansoor, for very nicely explaining to us. We can have questions. We can have questions from the students now. There's already one question that somebody has asked. Maybe you can just read it off.
Yes. So can Shram plot BBN graph plot predicts abundance of dark matter? So okay, so that I think you are talking about, I don't know how to go back.
Maybe you have to exit the full screen and then you can go back.
I don't know how to exit.
Hitting escape usually works.
Okay. Yeah, it was not working though.
Right. While Mansoor is digging up the plot to explain the answer to this question, if anybody else wants to ask a question, you can just raise your hands and I'll give you permission to talk.
Probably he's talking about this thing, that
Yeah.
whether we, so I'm not sure about it, that you will be able to predict this dark matter stuff, but from CMB, you can do that. In CMB you have the fitting model, the lambda CDM model, you have that.
Yeah, I don't think you can predict that from this particular plot.
From this nucleosynthesis. Yeah.
You can't see it. You can't see it in over here, but yeah.
It's all about an ordinary matter.
Right.
So Islamic perspective, Cosmological doctrines, so do we have more questions, or
does anyone else want to ask a question? If you want to ask a question, just raise your hand and I'll give you permission to speak. Okay, yeah, I think, well, Shoaib Munir has a question. Shoaib, go ahead.
Yeah, Mansoor. So from what I understood, I've not been in touch with this stuff for a long time. So you need SUSY breaking because that is going to give you radiative corrections to drive the shape of the potential. Did I understand that correctly?
Yeah, sorry, can you repeat?
So you need broken supersymmetry because that drives the shape of the potential.
Because that
to make it that gives you the Mexican hat shape of the potential, right? Because you said it's the radiative correction are responsible for the Mexican hat shape of the potential, right?
okay.
And then you also need
just give me a second. I mean,
sure.
Yeah, I think he's experiencing a lot of noise at his end.
Yeah, background noise with when there are kids, there's always
there was noise actually. So actually you need a almost flat potential. So if I mean you have non-zero potential, the supersymmetry will be broken. Yes. So during inflation, supersymmetry will be broken.
Right, and you also need broken gauge symmetry because the universe transforms from a flat from a symmetric universe to this so it goes from a so is there
two possibilities. Sorry.
So the question was, is there a connection between sorry, I don't know who's lagging, whether me or please go ahead.
Yeah, so regarding gauge symmetry breaking, there are two possibilities. In one possibility, during inflation, gauge symmetry is intact, so it's unbroken, and it breaks down after inflation. And in second possibility, you can also have gauge symmetry breaking during inflation. We usually consider supersymmetry breaking during inflation when we have topological defects like monopoles, things like that, in order to get rid of it. So
sorry, supersymmetry breaking or gauge symmetry breaking?
Gauge symmetry breaking. And supersymmetry will be broken during inflation in our framework, and it will be restored after inflation. It will be restored.
So, but there is there a framework?
And it will be broken then in the hidden sector.
Okay. So but is there a framework that links gauge symmetry breaking with SUSY breaking?
Yeah, in some way it is. You can say it is related, but I'm not sure.
Yeah, it just appears naively, but I'm not sure if it's actually been looked into this possibility. Yeah, I'm not familiar with literature in this field.
Can I interject at this point?
Yeah, let me answer this question. If the hidden sector, that symmetry is actually, we assume that the hidden sector which breaks the supersymmetry, and if that field which is responsible for breaking the supersymmetry is gauge non-singlet, so then you can have it. Like this, gauge anomaly mediation scenario and things like that. So in our scenario, actually, it's the gauge symmetry breaking is mediated through gravitational effects. Mostly Sugra. We are dealing with Sugra. If you are gauge mediated supersymmetry scenario, then you can have it. But here I did not talk about much about this hidden sector, how the supersymmetry is broken.
Sure. But, okay. Thank you.
If I might like to. From what I understood of Shoaib's question, he was, I thought his question was, is SUSY breaking needed to shape the potential? I thought that's what his question was. And from what I gathered from your answer was that SUSY breaking is happening because of this inflation.
Yeah, you need, if you are considering supersymmetric theory for inflation, you need supersymmetry to be broken during inflation because the potential is non-zero. If potential is zero, then supersymmetry is intact. At the end of inflation, your potential becomes zero. So SUSY is recovered. And then we have this standard scenario that SUSY is broken in the hidden sector later.
Great. Moise, can you go ahead and ask your question?
Yes. Thank you, Professor Mansoor, for a nice talk. I have two questions. One sort of not so fundamental, the other but more of a fundamental issue, at least for me. So one is when you're introducing these inflationary models, typical models, there's lots of parameters. And then you go ahead and fit them with typically two parameters there, the scalar to tensor ratio and the spectral index. So so can you make a statement on that, that you're perhaps introducing too many parameters per se initially, and then trying to fit it to a lower set of parameters? So that's my first question. And the second one, the fundamental one, is that supersymmetry has been promised for a long time, and it has not appeared yet, at least at the LHC, right? So some people call that the nightmare scenario. So in looking at that, is there still motivation to consider supersymmetric models?
Okay. So I mean, regarding, I think first question. So there are observables, CMB observables, and then there are parameters of your models. So there's a difference. So I was loosely speaking these observable to be parameters. So these are, I mean, this like spectral indices or this amplitude of scalar perturbation or other thing. I mean, these are observable which will be fitted by I mean, the Planck data. I mean, so we don't have much parameter in that sense. I mean, for inflation, we have actually maybe 3 parameters, let's say. Yeah. So scalar spectral index NS, amplitude ratio of this these two, because we don't see primordial gravitational waves. So we have this ratio tensor to scalar, which has a bound. And then third one is actually this amplitude of curvature. So this thing, and then we have parameter in our model. So that's a different thing. I mean, so in most of our model, I mean, we have, I think, I mean, not more than 2 or 3 models, 2 or 3 parameters in order to predict and in order to make the prediction for these observables, which are measured in the CMB data. I mean, by analyzing their anisotropies and things like that. And the second question, I mean, because I mean, to me, I mean, right now it will take some time. I mean, because supersymmetry, I mean, the very naive or simple models of supersymmetry are under tension. I mean, so it will take, I mean, I think, I cannot say for sure how much time, but it will take, I mean, to rule out, I mean, I should say, I mean, the rule out in the interest in supersymmetry, which is mostly due to this little hierarchy problem. That it will describe, I mean, it will, I mean, avoid that this little hierarchy problem. This is the big hierarchy problem. So if you have light spectrum, I mean, if you can predict light spectrum, then we okay. And when we don't see, I mean, this particles at, let's say, maybe, I mean, now people will go up to 100 tab, maybe shape can tell us, I mean, in the future collider machines. I mean, we'll be looking. It will take, I mean, maybe more than 10 years. I don't know how much. So completely rule out, I mean, this supersymmetry. So for me, I mean, it is an exciting, I mean, time to, I mean, to make your theories which will be tested at LSC, because the experiment are going on. So that I would say a good thing to look at this thing. Apart from string theories, I mean, which, I mean, you don't expect, I mean, their prediction to be testable. But in supersymmetry, I mean, the low scale supersymmetry, you can make testable predictions. So that's a good part of it. So I don't know if I answered your questions.
Okay, no, thanks. Yes, that does answer to some extent this. Yeah, thanks.
Shoaib, did
Oh.
you have another question, or is your hand
No,
still up?
Sorry, yeah, I just wanted to add to what Mansoor said. I mean, so supersymmetry, contrary to the common notion, it's not just a phenomenologically predictive theory. It's also a mathematical formalism. So as Mansoor was saying, it's not very successful in addressing the well, so far the little hierarchy problem, which everybody thought is the reason for supersymmetry to exist. But it's in you get grand unification only so far in supersymmetry. Superstring theory. So it naturally appears in in string theories, some string theories. So it's not just like a phenomenological model or framework. It's also a mathematically very attractive explanation of space-time. So supersymmetry itself is not ruled out yet. It probably cannot be ruled out in another 100 years. It's very specific models of supersymmetry, the minimal models that are in tension, as Mansoor pointed. But to say that they're causing tension in supersymmetry itself is actually not correct. Even if we don't find it in the near future, it's not, because it's also as a framework, it's very attractive. It's probably the most consistent framework that we have so far of just general explanation of the universe. It's not very likely that even if it doesn't explain the little hierarchy problem very well, it's not the underlying theory in nature. I hope that explained a bit more. I don't know.
Yeah, it has, theoretical interest in string theory. And when it comes from logical, point of view, you will, kind of lose interest. And lose interest, in terms of, because it was, present, to solve these hierarchy problems and things like that. So as, the bound on this particle masses, goes up, so in that sense it will goes into, otherwise you cannot rule out this supersymmetry ideas. You have high scale supersymmetry and things like that. I somehow connect this thing with the value of R. If you don't see, detect the, let's say, this tensor to scalar ratio in future experiment, still it will not kind of hurt the inflation, but it will lose some interest. You will lose some interest because you are not seeing something which which is very important for inflation. You are observing other things, but this is very crucial, this value of R. But still it will be allowed, but you will lose some interest if you see this value of R. In the future experiment, you detect the primordial gravitation wave, then it will be what people call it smoking gun signal for inflation. So similar, the value of R is going down, and in other scenario, the masses, the bounds on particle masses is going up and up, the bounds is. So
okay, I don't see anybody else's hand up right now, so so let's oh, wait a minute, I was just gonna miss Asif. Mansoor, I hope you don't mind sticking around with us for another couple of minutes. So
no problem. Yeah. So is there a question? I don't.
Yes, there's a question. Asif, you can ask your question. I've just given you permission to speak.
Excuse me, sir. I have a very basic question. How do we know for sure that we have dark matter in the universe? I mean, how is this matter detected? If it's dark and if it's not interacting with anything.
Okay, so actually this dark matter, it interacts through gravitational interaction, and also weakly it can it can interact with weak interaction, but mostly with gravitational interaction. So if light bends in some region and you don't see any ordinary matter, we know how to detect ordinary matter. So if you don't see, then this bending and also some other effects, it tells you that there is something. there is something, I mean, which is not interacting, let's say, in the same way which usually this ordinary matter does. I mean, so this is one way, and then there are also some direct, indirect ways, I mean, in which you can see that there should be dark matter. So gravitational lensing, this bending, and CMB data, if you don't include this dark matter component, you cannot explain this, I mean, the anisotropy. And then also there are also some other effects which I don't remember. I mean, maybe Rizwan can tell us.
No, I mean, I think you've really answered the
Yeah.
question nicely. I mean, you can begin by looking at the motion of stars towards the outer edges of the spiral galaxies. There, that's where dark matter was initially discovered. But then most recently, gravitational lensing studies will provide the most convincing evidence. My personal favorite is the bullet cluster, which is very easy to understand. And I encourage you to read up on it. The idea is very simple. If you see the bullet cluster is basically just an example of one cluster interacting with another one. There, basically what you actually see is one cluster going through another one. And when it's going through the other one, you see the bright part of the two clusters, you can see just move past each other. But from gravitational lensing studies, you can see that the mass is concentrated where you don't see any light at all. So basically gravity will, the effects of gravity are very, very obvious in that case. Well, Mansoor has been with us for the past hour and a half. Thank you very much, Mansoor, for taking time out to talk to us, to talk to our students. Great hearing from you. And thank you.
Thank you,
sir.